Hi everyone. In almost every electronic equipment you find switch mode converters. Switch mode converters which convert one DC voltage to another one. For instance, 5 volt to voltages which are necessary, lower voltages for your processor, like 3.3 volt or even 2.5 or 1.8 volt. In this video I'm going to just discuss with you the easiest one, the basic converter, which is called the buck converter, which converts higher voltages towards lower voltages. And when you understand the buck converter, you also easily understand the working of other converters like a boost converter or a CP converter or whatever kind of switch mode converter you want to use or apply. Well, to understand the buck converter, I have drawn a circuit diagram over here. And in the circuit diagram we have a voltage UN, which is the input voltage, which we are going to convert to a lower voltage, U out, over here. And in this circuit we have a switch over here, which is mostly an electronic switch like a MOSFET. And there is always an inductor in this circuit, an inductor L. And often a load is connected to that output voltage, and through that load there is a current flowing, and I have called that current I out. And that output voltage could be either a battery, for instance, which you wanna load, or it also could be, when you are talking about a processor board, it could be a capacitor like an electrolyte capacitor. Well, what happens when we close that switch? Suppose we have an input voltage of 25 volt over here, and we want to convert that to an output voltage, a 5 volt output voltage over here. When we close that switch, a current starts to flow, and due to the fact that there is an inductor in the circuit, we can define the voltage across that inductor L. And we can define that in the following way. We can say, well, UL, the voltage over across the inductor, is equal to L, the inductor value, times the derivative of the current through that inductor, which is IL in this case, the derivative towards time. So it's L times DIL dt. Okay, so this is a constant voltage. UL is a constant voltage because the voltage UL is UN minus U out. So we can put that in another way. We can also say IL, the current through that inductor, is equal to UL over L, and then taking the integral out of it. So UL over L, and then integrate that towards time. So I said UL is a constant voltage, so when we integrate that constant voltage we get a linear increasing current. And I will draw that with my red pencil over here. It starts, for instance, over here, and there it ends, and it should be a straight line like this. Okay, well, it was somewhat thicker and now it's thin. Well, thank you Microsoft for doing that. So it starts over here and it ends up over here. And suppose I open the switch at a certain point, then I can call this my on time, T on, and during that on time, so during this period, so during T on, my current starts to increase from this value to that value. So now look what happens when we suddenly open that switch, or when we take that MOSFET, which is a MOSFET in practice, when we take that MOSFET out of conduction. Due to that coil, to that inductor over here, that current IL will keep on flowing in that circuit. But because that switch is opened, it's not possible anymore for the current to flow. So IL is suddenly changed by means of a step weight by opening that switch. So the derivative of IL is very high. So we get a very huge voltage over here, and that leads to a spark across that switch, across that MOSFET, which will often destroy that MOSFET. So we have to define a path for that current IL to flow in a situation when the MOSFET is open. And we can do that by adding a diode over here in this way. And when we have placed the diode over here, you can see that when that switch is open, the current through the inductance can flow through the output voltage through that diode, and we have a circuit created to for that current to flow. So during the off time, so when the switch is opened, then the current will flow through the diode, and it will do something like that, also linearly. And so this is my off time, so I can call that T off, and the combination T on plus T off is my switching period, which is often called T. So that is complete switching time, the on time when the MOSFET is on, and the off time when the MOSFET is off. So okay, when having that, we can work out a couple of equations. So let's start by doing that. So I take my black pencil over here, and I still have my formula. UL is L times the derivative of IL over time, so DIL dt. So in the on situation, so in the situation I call the on situation in which the MOSFET is conducting situation, so when the switch is closed, we can say that the voltage across the inductance UL is equal to UN minus U out. So UL is UN minus U out, and that is equal to, I'm sorry for that, here we go, well, it doesn't want to do what I like to do, so go away please, thank you. So UN minus U out, so we get UN minus U out is equal to L times DIL dt. So we can also say, because it's linearly increasing, it's L times a delta I during the on time T on. Well, what is that delta I? That delta I is this value. Here we go again, that value. This is delta I. And the complete current is the current IL, of course. So now we can say in the on situation, U in minus U out is L times delta I over T on. We can do the same thing for the off situation. So for the off situation, the current is not flowing through the MOSFET anymore, off situation, but it's flowing through the diode over here. So it's flowing not through the MOSFET anymore, but it's flowing in that circuit, so through that diode. So UL is the voltage which is standing at this point, and suppose we have an ideal diode, then we can say this point is 0 volt, so UL is 0 minus U out. So UL is 0 minus U out, which is equal, U out is equal to L times, well, we see that the current is decreasing during the off time, so it's L time minus delta I, so I put the delta I over here and a minus over there, divided by T off. So now we have two equations, one for the on situation and one for the off situation. So what we can do now is, for both situations we can recalculate delta I. So for the on situation, which is situation number 1, in situation number 1 we can say delta I is equal to UN minus U out, UN minus U out multiplied with the on time and divided by L. And during the off situation, we have a more or less similar situation. We can say delta I is equal to U out times T off divided by L. So it's U out times T off divided by L. And what we've seen in the figure over here is that, of course, that delta L is has the same magnitude during the on time and during the off time. So we can put these two equations, we can set them equal to each other, and then we get the following. When we do that, we can say UN minus U out. Sorry for that. UN minus U out over L times T on is equal to U out over L times T off. So when we multiply both sides of the equation with L, which is of course not 0, then we get U in minus U out times T on is equal to U out times T off. Okay, working that out and putting every part with U in to the left side of the equation and with U out to the right side of the equation, we get U in times T off is U out times T on plus T off. And now we can say U out is well, I made an error over here. This should be T on, of course. Sorry for that. I do it in this way, right? It was UN times T on. So now we get U out is T on over T on plus T off times UN. And remember, T on plus T off is equal to the cycle time, which is the period time T. So we can also say it's T on over T, the complete period time, times U in. Remember that picture which we had over here? T on plus T off is equal to the period time T. So we can say the output voltage is equal to the on time over the period time times the input voltage. That division of T on over T is also called the duty cycle, D. So it's also D times U in. And remember, T is also equal to 1 over the switching frequency F. Okay, so suppose we started off with an example which I have shown over here. Suppose we want to have an output voltage of 5 volt and we have an input voltage of 25 volt. When that is the case, so when UN, here we go again, when UN is 25 volt and we want to have an output voltage of 5 volt, then we know that the duty cycle D has to be the output voltage 5 over 25 is 0.2. So suppose we have a switching frequency of that MOSFET of 200 kilohertz. Suppose the switching frequency, which is often very high, in order to be able to use a very low, a small inductor value. So suppose the switching frequency is 200 kilohertz, then we know that the period time is 1 over F, so it's 5 microseconds. And then we know that the duty cycle is 0.2, so we know that the on time is the duty cycle times the period time, which is equal to 0.2 times 5 microseconds, which is 1 microsecond. So in that case, in that example, we have a switching situation in which the switch, the MOSFET, is in conducting during 1 microsecond, and then it's not conducting, so the switch is open during 4 microseconds. So the current through the MOSFET is equal to the current IL only during the on time. So when I put the current through the MOSFET in the same picture, then we have the following. It's the same current as flowing through the inductor, but only at this point it's becoming 0. Oh, sorry for that. So it's going to 0 at this point over here. So this is, again, that is the current flowing through that MOSFET. So remember, due to the fact that during the off time the current is not flowing through that MOSFET, the average value of the current through that MOSFET is the duty cycle, which is 0.2, my example, times the current IL, which was 2 amps. So the current through the transistor, let's call it I switch, so it's a transistor or a MOSFET, so the current through that MOSFET, I switch, I call it, is also equal to the duty cycle times IL, which is in this case 0.2 times 2 amps, which was IL, which is 0.4 amps. Remember, it's the average value, I switch is the average value of the current through that MOSFET, which is very low, which is lower than the output current. So always keep in mind when selecting a MOSFET, the average current can be very low, but during the downtime, the maximum value of the current is of course I out, 2 amps in my case, plus halved delta delta L IL over here. So you should take into account that the maximum value of the current flowing through this transistor, through that MOSFET, could be much more higher than that average value. All right, when we have that, we can also calculate that value for the current through the switch by using the formulas for the power and the input and the power on the output. Suppose we have an ideal circuit, so we have an ideal circuit, which means that we have no losses in, for instance, the diode, and we have also, of course, an ideal inductor. Then we can say that the power at the input is equal to the power at the output. So the power at the input was U in times I in, which is equal to I switch in my case, I called it I switch, is equal to the output power, which was U out times I out. So when we want to calculate I switch by using the formula for the power, the equal power to the inside and the outside, we get the input voltage was 25 volt times I switch is equal to the output voltage, which was 5 volt in my case, times I out, which was 2 amps. And then we get 5 times 2 is 10 watt. So in that case, I switch is equal to 10 over 25 amps, which is 0.4 amps, what we also calculated over here. All right, and then of course we can also calculate the current, the average current through the diode, because using Kirchhoff's law, the average current through the diode is equal to the output current minus the input current. So the average current through the diode, I will write it over here, so I diode, the average value is I out minus I in, which I have called I switch, so it's I out, minus the average value of I switch, which is in this example 2 amps, minus 0.4, which is 1.6 amps. Alright, that's everything you have to know about the ideal buck converter, and by applying these kind of equations you can also calculate everything for a boost converter or even a more complex switch mode converter. Well, thank you very much for viewing this video, and I'll see you the next time.